Every massive complicated project, whether you're building a skyscraper or coding the next big app, it always starts the same way,
How that?
as just one single, totally overwhelming task. But what separates the amateurs from the pros is, well, it's the method of attack.
You can't just tackle the whole monster at once.
Exactly. You break it down.
And that decomposition, that is the essential magic trick of programming. For our deep dive today, our listener has provided a whole stack of sources focused on the very tools for that chaos
Yeah.
management. We're talking about user-defined functions.
So our mission today is to move beyond the simple definition. A function is just a block of code with a name.
Right.
We need to really master the mechanics. We have to understand the fundamental trade-offs, like how functions communicate, how they share data safely, and how we turn this potentially massive program into a collection of reliable, repeatable building blocks.
We're moving from just learning about it to actually building with it.
Yeah.
You know, every C++ program has that one required starting point, that function the operating system looks for,
Wow.
main. And every single custom function you define is built to serve that main execution flow, to make it more efficient, safer, and just infinitely more manageable.
Okay, let's unpack this with the ultimate question, the why. I mean, if I could just write all my code in a huge 500-line main function, when does the effort of actually defining these separate subprograms pay off?
Oh, it pays off almost immediately. The ultimate goal, as all the sources emphasize, is modularity.
Modularity.
Think about that 500-line main function. If one tiny calculation is wrong, or if you need to use that same calculation in 3 different places.
You're either debugging a nightmare spaghetti code or you're just copying and pasting.
Exactly. And you're creating instant redundancy.
And redundancy is technical debt. Right. Every copy you paste is just one more place you have to go back and fix a bug later.
Precisely. So by defining that, say, 30-line calculation once in a function, let's call it calculate shipping cost, you gain so much instantly.
Okay.
First, you get better design because you're forced to just focus on solving that one isolated sub-problem. And second, you achieve this profound code reuse. Call that function 100 times, the code is still only defined once.
And it cleans up the main execution point, too.
Yeah.
Your main function stops being this long scroll of detail, and it becomes a concise, readable list of instructions.
Yeah, like initialize database, then process user or data, then calculate final score.
It's abstraction in action.
And that is just huge for team development. If a big project is broken down into functions, team members can work on completely separate parts, separate files even, without constantly stepping on each other's toes.
It isolates the complexity.
It really does. And for you, the learner, that isolation is the key to reliability. If you update the logic inside one function, you know the rest of the program is safe, provided the function still works the same way.
It's self-contained and testable.
That testability is paramount. So when we talk about the mechanics, it's pretty simple. You define the function, usually outside main, in what's called the global scope, and then you just call it by name.
Right, and just to nail down the terminology here, there's a relationship at play. The function that starts it is the caller, and the one being executed is the callee.
And that relationship dictates everything about how data flows between them. It's a formal dance.
Speaking of that dance, let's talk about the plumbing. This gets us to how functions actually handle information. We're sort of borrowing from algebra here, right? Like fx.
Yeah.
We want our subprogram to take some input, do something with it, and give us a result.
And this is where programmers, especially new ones, often trip over the terminology. We have to be crystal clear on the difference between a parameter and an argument.
Okay.
A parameter, sometimes called a formal parameter, is the placeholder. It's the labeled slot in the function definition that's waiting for data.
So if I define a function like add in x in y, then x and y are the parameters. They're like little local variables ready to be filled.
Exactly. And the argument, or the actual parameter, is the real data you feed into that slot when you call the function.
So in add 5, 10, the numbers 5 and 10 are the arguments. They're the content that fills the slot.
That's it. And the rules for calling are strict. You have to pass the exact same number of arguments as there are parameters, and the data types have to match up left to right.
No exceptions.
No exception. Functions with parameters are just so much more useful because they're reusable. They can operate on any data you give them.
Which brings us to the next critical distinction, what the function actually does.
Right. We have void functions, sometimes called fruitless functions.
These just perform an action. They might print a message, save a file, something like that. But they do not send a value back to the caller with the return keyword. They just do their job and they're done.
And then we have the real workhorses, the type functions, or fruitful functions. A fruitful function is designed specifically to calculate and return a value. The function's signature itself defines the data type of that return value, an int, a string, whatever it is.
And here's an insight that I think is so important. Printing a result is not the same as returning a value. So why do expert developers almost always prefer a function that returns a value over one that just prints something?
Because a return value allows for composability. If your function returns the area of a circle, the caller can decide what to do with it. Print it, save it, or immediately pass it into another function that calculates, I don't know, the volume of a sphere.
A printed value is useless to the program itself.
It's totally useless to the machine. It only serves the human looking at the screen. A return value is immediately useful to the program.
And this ties right back into reliability and testing.
100%. Automated tests rely on functions returning a predictable value that the tests can check. If your function just prints something, it's way harder to test automatically.
So the fruitful parameterized function, that's the gold standard.
That's what you should be aiming for, absolutely.
Here's where it gets really interesting. So once we have that value ready to send, how does the data actually travel from the caller to the Cali? C++ gives us two very different ways to do this, and the choice involves a really fundamental trade-off.
It's all about safety versus efficiency.
Let's start with the default, which is pass by value.
Okay, so pass by value is the safest, but potentially the slowest approach. When you pass by value, the data of the argument is it's copied into the formal parameter.
So the function gets its own totally separate copy, like I'm handing you a photocopy of a document.
That is a perfect analogy. The advantage is absolute safety. If the function modifies its scribbles all over the photocopy, the original document I'm holding is completely untouched.
No side effects.
Zero side effects.
Yeah.
But the downside is performance. If you're copying a huge object, like a massive data structure with millions of elements, that copying process can eat up a lot of CPU time and memory. It's expensive.
Which brings us to the other way, pass by reference.
This is all about efficiency. Instead of copying all the data, we just pass the memory address, the reference of the data. We signal this with an ampersand, the answer symbol.
So no copy.
No copy. The function just gets directions to where the original data lives in memory.
So instead of the photocopy, I'm just giving you the address to the safe deposit box. Both the original argument and the parameter in the function are pointing to the exact same spot.
Efficiency maximized. We skip the costly copying entirely. But the risk is immediate, and it's a big one. The unintended side effect.
Oh.
If the function modifies the data using that reference, the original argument in the calling function is permanently changed.
Wow, okay. That sounds powerful, but also like a huge source of really hard to track bugs. If I pass a variable called user score by reference into a function that's only supposed to read it, but some bug in there accidentally changes it.
That change is now everywhere. It's live. And there's a constraint, too. You could only pass variables to reference parameters. You can't pass a literal value, like the number 42, by reference.
What?
Because a literal value doesn't have a stable memory address for the reference to point to.
Okay, so how do we mitigate that risk? If I want the speed of pass by reference, but the safety of pass by value, is there a middle ground?
There is. And this is where you start coding like a real pro. You use constant parameters.
Constant parameter.
You define a reference parameter as constant tn. That makes it a read-only alias for the original data.
I see. So we get the speed of passing the memory address, so zero copying cost, but the compiler guarantees that the function cannot modify the original data.
Exactly. It's the engineering compromise we need.
Yeah.
Speed without the risk of those nasty side effects. It's often called a zero-cost abstraction because you gain safety without losing any performance.
That is genuinely clever. And you mentioned earlier that C++ functions can only return one value. It sounds like this reference technique can help us break that rule, can't it?
It can. It's a really ingenious workaround. Let's say you have a void function and it needs to calculate both an average and a standard deviation. You can't return both. So instead, you pass the average variable and the deviation variable into the void function by reference. The function then modifies those external variables directly.
So when the function finishes, the caller now has access to two new updated values in its own local variables.
And you've effectively gotten two results back from a void function.
That makes perfect sense. Okay, let's talk organization. Often we want to put main right at the top of the file so it's clean and readable. But the compiler reads top to bottom, and it insists that a function has to be defined before it gets called.
So we run into this classic problem. How do we tell the compiler about a function that we haven't written yet? And the solution is the function prototype.
Or the function signature.
Same thing, yeah. It's basically a contract.
Ah.
The prototype is a declaration that says, hey, trust me, the body of this function is coming later, but for now, here's its name, what it returns, and what parameters it needs.
It's like an advance warning.
It is. And crucially, the prototype only needs the return type, the name, and the types of the parameters. The parameter names themselves are optional there.
Why is that?
Because all the compiler cares about is the data structure for the call, not what you decide to name the variables inside the function body. This lets you keep main at the top and really improves readability.
That idea of organization leads us right into a major boundary system in programming, scope.
Scope, right. Yeah.
Scope defines the area of visibility. If I declare a variable or a function, where can it actually be seen and used?
The sources have a great visualization for this. They talk about scopes as nested frames, like Russian nesting dolls.
Okay.
The largest outermost doll is the global scope. Anything declared here, outside of any function, is visible everywhere. Most of your functions live here.
Then we step inside a function and we hit local scope. This is everything defined inside that function, including its parameters.
Right, and those are only usable within that specific function. They vanish when the function ends.
And finally, the tightest frame is block scope.
The smallest all. It's the area inside any set of curly braces, like inside an if statement or a for loop. A variable declared there has very, very limited visibility.
So what if I have a variable named count in the global scope, and then I declare another variable, also named count, inside a local function? How does the compiler know which one I mean?
That's the name resolution process. The compiler is very logical about this. When it sees a name, it looks in the current scope first, the innermost doll.
Right.
If it doesn't find it there, it searches the frame it's immediately inside and so on, working its way outward until it hits the global frame.
Which means local variables always take precedence. They hide the global ones.
Which is exactly what you want. It's a safety feature that protects you from accidentally modifying global data.
That hierarchy maintains order.
Okay, let's scale up again. We've got our function, but we want it to be even more flexible. Say I want a function called add, but sometimes I need to add two integers, sometimes an integer and a double, maybe even concatenate two strings.
Right. And defining a separate function, like addinton, addedlent, for every combination would just be a maintenance nightmare.
Total nightmare.
So we have two great solutions for this. The first is function overloading. Overloading lets us reuse the same function, name, add, as long as the functions have different prototypes.
Right. The compiler looks at the arguments you pass, say, two integers, and it automatically figures out which version of add you meant to call.
So it's looking at add dint versus add double-double.
Exactly. It uses the number and type of the arguments to tell them apart. But even this can get a bit cumbersome if you have dozens of different type combinations you need to support.
And that's where the truly elegant solution comes in.
Function templating.
Right.
Templates are the way to write completely generic, reusable code. Instead of specifying int or double in your function signature, you use these placeholders, these template parameters, often just called T for type.
So you write one function definition using these generic types, and the compiler automatically generates the specific versions of that function that it needs based on how you call it.
You write the logic once, and it just works for integers, floats, strings, even your own custom data types, without you having to repeat that function body over and over again. Templating is where we move from just breaking down a problem to solving it generically.
Which is the hallmark of modern reusable code.
Absolutely.
So what does this all mean? We started with the foundation, the basic required function main, and we learned how to build these reusable, testable subprograms. We mastered the critical distinction between passing data by value, the safe, expensive copy,
versus passing the memory address by reference, the fast but risky pointer.
And most importantly, we learned that we can get the best of both worlds by using const references to get speed and safety.
And tying it all back to the practical application for you, the learner.
Yeah.
All those tasks like calculating BMI or area or time conversions, they rely entirely on having reliable, fruitful functions. If you choose to return a value instead of just printing it, you make your code inherently easier to test, which lets you prove its reliability automatically. And that reliability is the whole point of modular design.
And as you focus on getting your functions to return that perfect, reliable value, there's one subtle but really crucial pitfall of structure to watch out for. And that is dead code.
Dead code. It's any segment of code in your program that the computer will never, under any circumstances, execute.
And in functions, the most common way this happens is by returning too early.
Exactly. If you have a line of code after a return statement, that line is unreachable. It's impossible for the processor to ever get to it.
That's a fascinating side effect of structure. So our challenge to you, the learner, is this. Look closely at your functions. Are you ensuring that every single line you write serves a purpose? Or have you, maybe inadvertently, cut off the execution path with an early return? Keeping those function bodies tight and purposeful is really the final detail of perfect function design.